more discussion with all of you in hope that all of you can get more exposure about how to solve questions in these selected topics. Now, this is also one way for you to do revision and prepare yourself for the final exam in the end of the semester. Now, today's session, we will go through three topics. First is the UV transformation. Okay, since all of you have actually gone through this UV transformation in your midterm test before, so most of the information should still be clear, and I hope that concepts are still familiar to you. All right, without further ado, okay, let us consider a very quick short summary about the UV transformation. Now, again, in the questions of the UV transformation, you will always be given 4 equations. And under these 4 equations, we will try to recognize and pair 2 similar functions into one set and the other 2 functions into another set, so that later we can transform both of them into U and V respectively. So again, the UV transformation, there are a few things that you have to keep in mind. First and foremost, the UV transformation involving Jacobian. Now, this is the Jacobian that I believe all of you are already familiar. All right. Under this case, we always use the technique 1 over the partial differentiation of U with respect to X, partial differentiation of U with respect to Y, next partial differentiation of V with respect to X, and then with respect to Y. So in the end, you just need to keep track that the UV transformation, the Jacobian function, is computed by multiplying. Here, if I denote A, B, C, D, then the matrix transformation determinant is given by A multiply D minus B multiply C. So this is the Jacobian term. And sometimes the U and V will be given and sometimes they are not. So you just need to recognize the function and pair them up. Now, under this UV transformation, I actually picked 2 questions from the tutorial slides. Okay, the first I want to go through with you is question number 2. Now, when you try to solve the UV transformation, please be a bit flexible. Sometimes you have to twist your mind a bit to recognize how to make everything into UV from XY. So here, second questions from the tutorials, from the lecture slide. Now use the transformation U equals to x squared minus y squared and V equals to y over x to set up the integral, double integral, y over x dy dx in terms of U and V for the region R in the first quadrant lying between the graphs of x squared minus y squared equals to 5, x squared minus y squared equals to 3, x equals to 2y, and y equals to 0. Now, just to give you some guarantee, in UV transformation, you do not actually need to sketch any graph. Even if you are not familiar between the region R in the first quadrant between the graph, that is fine. Like I said, the most important part is you should be able to recognize 4 equations and how to pair them up. So in this case, we have the equation x squared minus y squared equals to 5 and x squared minus y squared equals to 3. Now, whenever you try to write out the equation, immediately you should be recognized some pattern. Here, U equals to x squared minus y squared. In other words, you immediately can already transform the first 2 equations into U. Because x squared minus y squared equals to U, this is just U equals to 5 and U equals to 3. Having 5 and 3, then this gives you the integral of du having lower limit 3 and upper limit 5. Now, when you try to make it into the limit interval, make sure you arrange from smaller value to the larger value. Now, since you know the first two equations you can pair up into U, you should convince yourself the remaining two pair you will make it into V. Now, these next two pair may be slightly confusing at the beginning because we are having equations x equals to 2y and then y equals to 0. Now, the remaining pair, you should actually make it into V because again, we are doing UV transformation. So set pertama di atas dah jadi U. So set yang kedua di bawah hendak jadi V. Now, since V equals to y over x, try to do something here so that you get the form of y over x. Well, the first equation should be easily done. You just need to swap the position of these two, x and 2, becoming 1 over 2 equals to y divided by x. All right, now again, simply swap this position, x and 2, to left and right side. Now you immediately see the first form, y over x equals to 1 over 2. So you obtain the first V. Now for the case of y equals to 0, well, you just need to also again manipulate a bit. From y equals to 0, you want to make it into y divided by x. What you do is you simply divide both left and right hand side by x. So here, y divided by x equals to 0 divided by x. In the end, this is also equals to 0. So now you finally obtain y over x equals to 1 over 2, y over x equals to 0. Therefore, this will become your V transformation. Like I mentioned just now, sometimes you have to twist your mind a bit so that you can actually change everything into the U and V variable. So now having this interval, you can arrange integral for dV, arrange from smaller value to larger value. All right, so this is the reason why I pick question 2 to go through with you, because sometimes you may need to manipulate the function a bit for you to actually get the interval correct. So this should be the first thing that you collect. Now, second, as usual, we will compute the Jacobian transformation, Jacobian term. So the Jacobian term of xy transform into u and v by the definition and the formula, it should be 1 over the determinant, differentiate u with respect to x, differentiate u with respect to y, differentiate v with respect to x, and differentiate v with respect to y. Now, the second reason why I picked this question to go through with you, because so far we rarely see the transformation having fraction. Let's say here v equals to y over x. Now here you notice that later you may need to partially differentiate with respect to x and with respect to y. So it will be good for us to go through this exercise slightly here. Now by the Jacobian term, u equals to x squared minus y squared. So let me do it here. U equals to x squared minus y squared. And therefore, if I try to partially differentiate u with respect to x, I actually obtain 2x. Similarly, if I try to differentiate u with respect to y, be careful, this is minus y squared. It should become negative 2y. So they will fit the first row position here, 2x and negative 2y. Now, on the other hand, for the equation, function v equals to y over x. Now, in case if you want to perform differentiation, I will highly recommend you to change the way of writing y over x to become yx power negative 1. Because we are now going to differentiate fraction function, so changing them into power rule will make the differentiation slightly easier. So here, if you try to partial differentiate v with respect to x, So x power -1, if you differentiate, it becomes -1 y x power -2. If you rewrite them again, it becomes -y over x squared. Again, -1, differentiate, x power -2. Y still remain there because we are now differentiating x. Now, if you try to differentiate the same function v with respect to y in this case, y is differentiated into 1, therefore the differentiation will be only x power -1 or simply 1 over x. Now, this is the part that you also have to be careful, just in case later in the final exam, you are given some function in fractions that when you want to partially differentiate them, change into index law so that you can use the power rule differentiation to differentiate them easily. So here, dv over dx, negative y over x squared, here 1 over x. So everything has been set up for the Jacobian transformation, the Jacobian computation. Finally, time to compute the determinant. So again, 2x multiply 1 over x. Again, 2x multiply 1 over x minus -2y multiply -y over x squared. -2y multiply -y over x squared. Okay, also be careful since now we are involving quite a few of negative sign and also fractions and non-fractions term there. So be careful. Here, 2x and 1 over x can be simplified. So this gives you 1 over simply 2 minus -2y multiply -y over x squared actually gives you -2y squared over x squared. Now, in terms of the Jacobian transformation, sometimes when we compute the Jacobian term, we may obtain only numbers. Sometimes we may still obtain some variables. Now, in the case if you still obtain some variables, then try to pause a while and think about it. Can you actually convert the x and y in your Jacobian straight away into u or v? If you can do so, then you do it here. Let me repeat. Now, sometimes when we compute Jacobian transformation, the J term, sometimes we may have only numbers. Sometimes we may obtain more variable x and y. Like in this case, I still have y squared over x squared. Now try to pause for a while and then relate it back to your UV. Can you directly convert x and y into u and v here? If you can, then do it. Now, if you refer to v equals to y over x, it seems like the form and the pattern is already similar. Here, again, v equals to y over x. If you simply square the v, now it becomes y squared over x squared. In other words, this part here can actually be transformed further into 1 over 2 minus 2v squared. So now everything is in variable u and v. This is the Jacobian term that you obtain. All right. Now, let's say in the case, if you are not able to do anything here, don't worry. Okay, you can still substitute everything into the formula first and see whether you can perform cancellation. Now, in the next question, I will explain to you what do I mean by if you cannot do anything here yet. All right. So again, in this case, we notice that having y squared over x squared, I can further transform it into simply v squared here. So this is the Jacobian term that I have. So having Jacobian, having u and v, the interval, it's time for us to set up the uv transformation from the original question here. double integral y over x dy dx. So in the next slide here, let me begin by setting again the original questions, double integral y over x dy dx. All right, in terms of setting, usually or as usual, I will always recommend students to actually fit in the Jacobian term first, because this is the one that students always overlook. When you open the double integral, immediately you fit in the Jacobian 1 over 2 minus 2b squared modulus. And that du dv. Now, just to also remind you again, either you want to use du dv or dv du, it doesn't matter. So it depends on your own convenience. All right. So you can do this later on your own and see what is the effect. So here I remain du dv. Now, please be careful. I set du in the front place. Therefore, the interval should be from 3 to 5. dv outside, therefore dv should be 0 to 1 over 2. So y over x is transformed into into v. So again, y over x into v, dy dx Jacobian transform 1 over 2 minus 2v squared du dv. So everything has been set up. Then next, you can continue by the integration. Now, in the integration process, it's up to you. Whenever you want to simplify, you want to factor out anything, go ahead. So here, let me begin by actually factor out 1 over 2 from the Jacobian. Since this is positive, if you look carefully, I can actually factor 1 over 2 out, leaving you 1 over 1 minus v squared. Okay, having common factor. And now it gives me 1 over 2 integrate 0 to 1 over 2 integrate 3 to 5, giving me v over 1 minus v squared du dv. And remember, in our first integration is with respect to u. So we are targeting the u variable. In the current integration, it seems like we do not have any u variable there. This is just like a constant in u variable. Therefore, this integration should be quite straightforward. From 0 to 1 over 2, I put v over 1 minus v squared aside. Integrate du gives you the variable u back. So this is 5 and 3. All right, so whenever you are not integrating that variable, put aside first, settle whatever you have. Therefore, integrate with respect to u gives you u. So here should be quite straightforward, because if you substitute upper limit and lower limit to it, you actually get 1. All right, so let me also do this computation out. As you can see, substitute 5 upper limit minus substitute 3 lower limit. Oops. And that 5 minus 3 equals to 2, 2, and 1 over 2 can actually simplify to each other. All right, so this is the simplification process that I do immediately here. Now, if you look carefully, whatever left in the next step here is the integration from 0 to 1 over 2 v over 1 minus v squared dv. Now, in your mind, you should remind yourself this integration is not simple. You cannot use simple power rule to integrate. If you cannot use simple power rule to integrate, recall yourself, your next technique is the substitution technique. So by right, you should already aware substitution technique means that we will let the most complicated function to be substituted by another new variable. So here, let me use z to denote 1 minus v squared. That is, I substitute this denominator by 1 minus v squared, and therefore differentiate z over differentiate v gives you negative 2v. All right, rearranging the equation, dz divided by negative 2v equals to dv. Replace the current computation into it, integrate from 0 to 1 over 2, v, nothing changed so far, over 1 minus v squared has been replaced by z. dv, here dz over negative 2v. Now, whenever you perform the correct substitution technique, eventually v and v will simplify each other immediately, giving you negative 2 can be putting out, negative 1 over 2, integrate from 0 to 1 over 2, 1 over z, dz. Right? Don't forget, there's still negative 2 at the denominator here. Pull out the constant coefficient. So here, integrate 1 over z should be ln z. So upper limit 1 over 2, lower limit 0. Now, whenever you perform the integration, do not forget in the end, you replace back the variable z into v, because originally z is 1 minus v squared. So now I will return z into ln in the bracket 1 minus v squared. Now you can properly substitute 1 over 2 and 0 into the integrand. Substituting half into it, giving you negative 1 over 2, open a big bracket, ln in the bracket 1 minus v squared is 1 over 4. Minus ln, substitute lower limit into it, 1 minus v squared is actually ln 1. So ln 1 by identity from your calculator, this is equals to 0. 1 minus 1 over 4 is 3 over 4. In the end, negative 1 over 2 ln 3 over 4 is the integral output from this UV transformation. So let's check whether it is the same as the answer given in the tutorial questions. Negative half ln 3 over 4, yes indeed. All right, so one point or one hint probably I would like to share with all of you is that most of the time, I mean most of the time, not always, most of the time in UV transformation, they will always involve one technique of substitution in the integration. Because whenever we transform x and y into u and v, sometimes the structure can be slightly complicated after changing u and v, and you need to do some techniques in the integration for you to integrate either u or v successfully in the end. Just to also let you know, all the tutorial questions in the lecture slide are actually taken from past year questions. It's just that maybe they are a long time ago, 5 or 6 years back. So these are how actually the questions will be asked in the final exams. All right, next, second questions also about UV transformation. As you can see here, the form will be slightly similar. This is question number 4 taken from the lecture slide. Now use the transformation u equals to x minus y and v equals to x over y to show that the absolute value of the Jacobian is y squared over x minus y. Hence, evaluate the double integral x over y power 3 dA, where R is the region in the first quadrant bounded by y equals to x minus 3, y equals to x minus 1, 3y equals to x, and 5y equals to 2x. Again, under UV transformation, you have 4 sets of equation. First thing first, collect them. We have y equals to x minus 3. We have y equals to x minus 1. If you look carefully, they are similar. Y on the left-hand side, x on the right-hand side. If you match, it is also very close to u. U is y minus x. So let us take a bit of time to rearrange the term here. If you swap the integer and y on left and right hand side, you will obtain 3 equals to x minus y. Here, swap -1 and y, you get +1 equals to x minus y. Now, this pair becomes your u. And that your u equals to 3, your u equals to 1. This gives you the limit integration from 1 until 3 with respect to u. The first pair is for u, therefore the second pair will be for v. So here we have 3y equals to x. We have 5y equals to 2x. Look carefully, your v function is x divided by y. Therefore, from here, do a bit of rearrangement. 3 equals to x divided by y. By just shifting y to the right-hand side, divide. So x over y gives you 3. Similarly, 5y equals to 2x. So here, y and 2 just simply swap across the position. We have 5 over 2 equals to x over y. So now x over y is represented by the transformation of v. So v equals to 3, v equals to 5 over 2. Now make sure you can differentiate between 3 and 5 over 2, which one is larger. Sebab yang paling kecil akan letak di integral bawah, yang paling besar akan letak di integral atas, limit. So 5 over 2 smaller, 3 is larger, therefore this is the integral for dv. Now sometimes the question can also ask in this way. The question has already give you the Jacobian term, but you need to show whether the Jacobian is indeed y squared over x minus y. In other words, Jacobian has been given. You just need to redo the process and show that, yes, this is correct. Therefore, we will now show that this Jacobian is indeed the correct one. So the Jacobian of xy transformed into uv is given by 1 over the determinant, differentiate u with respect to x, differentiate u with respect to y, differentiate v with respect to x, differentiate v with respect to y. All right, so as usual, first thing first, let's look at the u function. The u is given by x minus 1 minus y. Therefore, differentiate u with respect to x. Differentiate x, you obtain 1. Differentiate u with respect to y. Differentiate negative y, you obtain -1. So here, 1, -1. Be careful again if there's any negative sign. Second, if you look at the function of v equals to x over y, like we have learned in the previous question, it would be good for us to change it into the power rule so that later when we perform differentiation, it will be slightly easier. So here, if you differentiate v with respect to x, you only target x, so x becomes 1, but you still have y power negative 1. So this is 1 over y. But when you differentiate v with respect to y, y power negative 1 is differentiated into negative 1 x y power negative 2. This is just negative x over y squared. So fit in the position, this is 1 over y, this is negative x over y squared. So now we are ready to compute the Jacobian and see whether the answer is indeed the same. So by the Jacobian determinant, first 1 multiply negative x over y squared. We have negative x over y squared minus negative 1 multiply 1 over y. We have negative 1 over y. Okay. Simplifying this term, we have negative x over y squared plus 1 over y. Now, look carefully. The denominator y squared and y, it's not the same. So let us do a bit of common denominator, giving us negative x plus y over y squared. Then 1 over fraction, the denominator y squared will actually brought up, giving you y squared over negative x plus y. Now, if you compare to what Jacobian that you compute now and the answer that it asks you to show, you are actually very near. But you notice that denominator x minus y, what you have is minus x plus y. What is actually missing here is that you have not shown the absolute value yet. Now, I hope, let me flip back the notes a bit. I hope you still remember when you plug in Jacobian inside the UV transformation, this part is actually the absolute value. Negative will be transformed and convert into positive sign. So you just need to add on this gate in front and behind to show the proper result. All right, so remember this, y squared over negative x plus y, because I will do it in the next slide. So just now, we stopped at the Jacobian equals to y squared over negative x plus y. Now, how do we show the absolute value? Okay, the absolute value is simple. You just need to first put the gate in front and behind. Now, whenever you put the gate in front and behind, then you have to do something. That is, if the first term is having negative sign, factor that negative out. I repeat, if there is a negative sign in the first term, let's say here, negative x plus y, faktorkan negatif 1 keluar, factor that negative out. So this is to say that in the next step, this is y squared over, if you factor out negative 1, inside the bracket, you have x minus y. Because factor negative, this becomes positive. Factor negative plus becomes minus. Now, if you can understand the steps so far, then if you put the modulus, now this negative 1 will becomes positive. In other words, now negative 1 under this modulus, negative becomes positive, and therefore that negative 1 will disappear eventually, giving you y squared over x minus y. I believe some of you may need a bit of time to actually understand this part. Let me highlight again. This -1, when you meet the modulus absolute gate, it disappeared because -1 becomes positive. So now, in the end, you have shown that the Jacobian is y squared over x minus y. So just to also let you know, sometimes the question may also show you Jacobian and ask you to prove it. All right, so having everything done, then x over y power 3 dA. Now again, if you look carefully here, y squared over x minus y, our Jacobian still contain variable y and x. All right, like I mentioned just now, if you can convert into u and v, then you do it immediately. If you cannot, leave it first. Now, if you match y squared over x minus y, the first thing you can convert is actually u, because u equals to x minus y. Therefore, from here, you can change into y squared over u immediately. Y squared, if you look carefully, no matter how you try to rearrange and try to manipulate, you still have no idea how to make only y squared appear. Sebab u sama dengan x tolak y, v sama dengan x over y. Dua-dua pun ada x dan y serentak. If you only want to get y squared, nampak macam tak mungkin. So if this is the case, don't worry. Let it be first, and then you convert or transform everything into the problem and see how it goes. In other words, kalau tak boleh transform terus, jangan risau, kekalkan dulu, then put everything into the question. The question is double integral x over y power 3. So now, double integral x over y power 3 dA. Under UV transformation, we will make it into du dv. That is open two interval, followed by Jacobian, here y squared over u du dv. So the du interval previously we have set up to be 1 to 3. 1 hingga 3. V is 5 over 2 to 3. Now for y, x over y power 3, we also need to manipulate. If you look at the u and v transformation, we have v equals to x over y. So in this case, you might need to think x over y, you extract out from here, leaving you 1 over y squared. Okay, x over y power 3, you split into x over y, multiply 1 over y squared. Now you should be able to notice whatever you cannot solve y squared just now can actually be simplified with the original question. So x over y is actually v. So this is v over u du dv. Now this computation should be straightforward and easier now, because you have reduced and transformed all the terms into u and v. Now integrating with respect to u, remember 1 over u is integrated into ln u. So v not related, put aside, integrate 1 over u, you obtain ln u. Substituted upper limit 3, lower limit 1, dv. So this gives you integrate 3, 5 over 2, v in the bracket ln 3 minus ln 1. And we know that ln 1 is equals to 0. So ln 3 is the constant, this constant you can actually pull out from the integral. Now finally integrate from 5/2 to 3. V with respect to V should be simple. This is just a normal power rule integration. V squared over 2. Substituting upper limit 3 and lower limit 5/2. So from here, I will go slightly quickly because this is just some simple computation that you have done many times before. Substituting 3 inside. 3 squared over 2 is 9/2. Minus, substitute 5/2 inside. 5/2 squared is actually 25/4/2. So if you solve this fraction using your calculator, multiply ln 3 later, you should be able to obtain the exact same answer here, 11/8 ln 3. So actually, again, these two demonstrations is just to let you see the transformation involving different Jacobian. Sometimes you may need to twist your mind a bit for you to actually get the full transformation of U and V. So this is the part that probably may trick some of you for the first time. But if you are already quite familiar with playing around with U and V function, suppose you should be able to handle them quite easily in the end. Again, practice is the key. So only 2 questions. Yes, I would like to go through with you just a quick revision and also to recap some of the things that you have learned before in UV transformation. Okay, as usual, any questions, or if you want me to demonstrate some questions that you are not familiar with, you can always let me know in the chat box. Now, after the UV transformation topic, the next will be mass and center of mass of lamina. Now, this is the topic that I somehow quite worried because this is the topic actually right after your test, and I'm not sure are all of you actually still remember about mass and center of mass. So just to recap a bit, under the mass and center of mass of lamina, these are the only 3 formulas that you need to remember. Well, they will be given in the final exam later. There will be a list of formula. Yes, mass of lamina, the formula are provided in the exams. You just need to know mass M is given by double integral density function area. Center of mass, there should be 2 coordinates, x bar and y bar. X bar is 1 over mass M that you computed. Here, double integral x multiplied density function. Y coordinate is the similar formula, 1 over m, double integral, you multiply additional variable y to density function. Again, the part that I highlight, please be careful, because this is always the first careless mistake students did in the mass of lamina. All right, so if the question talks about the centroid or constant density, then we say that that constant density has the constant value 1. All right, basically, mass of lamina, these are the only 3 formulas that you have to remember. dA under double integral can be either dx dy, can be either dy dx, or under polar coordinate, it can be r dr d theta. Okay, this is double integral in chapter 2. Now, if you understand the formula again and record them, then we can move into some things to keep in mind. Again, dy dx, dx dy, how to move the graph left to right, lower to upper, in circle, r dr d theta, polar coordinates. All right, this is tutorial questions from the slide. Question number 2. Well, figure 1 shows the lamina bounded by x-axis and lower half of circle x squared plus y squared equals to 2. Clearly, you know this is circle, therefore you need r dr d theta. Okay, this is the area of the circle, lower half. So by right, when you look at this graph itself, you should already able to tell yourself, this is the graph having theta rotate from pi until theta equals to 2 pi, because the rotation is actually in anti-clockwise direction. Second, x squared plus y squared equals to 4. You should be able to convince yourself the radius is equals to 2. If you can get these two ideas, basically you can proceed to compute the mass of lamina and center of mass easily. Now look at the question. Find the y-coordinate for the center of mass for the lamina if the density function is square root x squared plus y squared. Now, by the formula for y-coordinate for the center of mass of lamina, okay, again, the question requests y-coordinate. By the y-coordinate, which means we are now looking for the integration. Okay, y bar equals to 1 over m double integral variable y multiply density function of xy with respect to area. Now this is the formula for y-coordinate, and you know that you need this mass m. Now, in other words, whenever you want to find coordinate, you must first compute the mass m. So mass m is simply double integral density function rho in xy of dA. So to make everything clear, for every questions in mass of lamina, first thing first, compute m. You need to know the mass. The mass is always double integral of density function. Now, since you know the density function is given by square root x squared plus y squared. So you can fit into here first, x squared plus y squared dA. Next, you should also know this is actually a circle. Therefore, we will use polar coordinate system to solve the problem. Polar coordinate recorded is given by double integral r dr d theta. The inner integration is radius r. Look carefully, we have found r equals to 2. Therefore, integration should be from 0 to 2. The outer integral, theta, theta is the rotation of the angle we have seen just now from pi to 2 pi. Oops. So don't forget, the density function should also be polar transform. Now, by the circle equation, recorded circle equation, x squared plus y squared is equals to r squared. Therefore, this part here can be transformed into square root of r squared. Right? Circle equation, x squared plus y squared equals to radius squared. Now, square root of square can actually eliminate each other. Therefore, in the next step, you should obtain quite a very simple structure of the mass. 0 to 2, this is simply r squared dr d theta. So next, integrating with respect to r. So giving you r power 3 over 3, substituting upper limit 2, lower limit 0. So this will give you the next step, integrate pi to 2 pi substitute 2 into it. 2 power 3 gives you 8, 8 over 3. Substitute 0 into it, 0. So 8 over 3 d theta. And finally, this gives you 8 over 3. Integrate with respect to theta, you obtain one theta variable from 2 pi and pi. So this gives you 8 over 3 in the bracket 2 pi minus pi. And hence, your mass m is 8 over 3 pi. So again, these are exactly finding the double integral. In polar coordinates, remember, all x and y will be changed into polar form. X squared plus y squared is a circle. Now, I just want to remind all of you again, because some of you still confused. Now, just make everything simple and straightforward. Whenever you see the keyword circle, semicircle, circle equation, don't think too much. Make everything into r dr d theta. That is the only way to solve polar coordinate for circle equation. Kalau bukan circle, then dx dy, dy dx. Once you notice the keyword circle, immediately r dr d theta. We're not done yet because we just obtained the mass. This is the mass that we need to fit in this position. Therefore, continue finding the y coordinate here. So 1 over m is just 1 over, in the big bracket, 8 over 3 pi. So this is the m that we found here. Well, if you understand how to solve, how to find m, the exact same integral you will plug and copy paste into your y. In other words, any double integral that you use in finding m, the exact double integral you just copy and paste into the coordinate. So sini from pi equals to 2 pi will be the same. From 0 to 2 will still be the same. R dr d theta will still be the same. Density function here will still be the same as this. Square root of r squared. So you know the raw density function is r. The only one that you have to be careful is the additional variable y inside. Yes, when you compute the coordinate for the center, please be careful with the additional variable. Ada satu extra y di sini, y dalam polar form adalah r sin theta. Y is r sin theta. Raw density function, dA, we have already converted here. Therefore, just copy and paste into your next. So now everything can be simplified before you move further. 1 over 8 over 3 pi is actually 3 over 8 pi. Integrate from pi to 2 pi. Integrate from 0 to 2. R multiply R multiply R. They are actually R power 3 sine theta here. And then dr d theta. All right, so first thing first, we integrate with respect to r. 3 over 8 pi still remain here. Coefficient, nothing involved. So from pi to 2 pi. Here, r power 3 is integrated into r power 4 over 4. Substituting the upper limit 2 and lower limit 0. Sine theta d theta. All right, so here, do a bit of mathematics. 3 over 8 pi. Integrate pi to 2 pi. So substitute upper limit 2 into it. 2 power 4 divided by 4 actually gives you 16 divided by 4 minus 0. So here, if you compute slightly, you obtain 4. Okay, 2 kuasa 4, 16. So 16 bahagi 4, kamu dapat sin 4 sin theta d theta. So here, 4 and 8 can actually simplify the coefficient, giving you 3 over 2 pi. Lastly, sin theta can be integrated into negative cos theta. So don't forget, sin theta is integrated into negative cos theta, and this is substituted using upper limit 2 pi and lower limit pi. So please, any computation involving the trigonometric functions, compute carefully. Negative cos of 2 pi minus in the bracket negative cos pi. So taking your calculator, if you try to press cos of 2 pi, you should notice it gives you positive 1. So negative cos 2 pi is negative 1. So plus minus and minus gives you plus. Cos pi is actually negative 1. So that's why if you simplify this whole expression here, eventually you obtain negative 3 over pi as the y coordinate for the center of mass of Lamina. All right, so as usual, in the mass of Lamina and center of mass of Lamina, the essential part is actually the first setup in computing the mass m, double integral of the density function, and the coordinate for the center. If the coordinate y is asked, therefore it will be 1 over m, double integral y multiply density. If you are asked about coordinate x, therefore it will be 1 over m, double integration, variable x multiply density function. In other words, please make sure you take note of the additional variable inside the coordinate for the center. Right, just to make sure the answer in the end is y bar is equals to negative 3 over pi. Okay, mass of Lamina is quite straightforward, and every time in every semester there will be one question asked in the final exam. Since you have not gone through this in the midterm test, so please focus and practice yourself more in finding the mass m and the coordinate x and y. So let's see one more question. This can also be the way the mass of Lamina can be asked. Now, this question is actually from the previous, the recent February 2025 past year final exam questions. Sometimes the questions can be asked in many ways. So for example, here, the density of a mass of a lamina is given by density rho k multiply 1 over square root of y. First, sketch and shape the region of a lamina bounded by the graph y squared less than or equals to x less than or equals to 4y and 0 less than y less than 4. Okay, sometimes the question may ask you to sketch the graph. Well, this is doable because we are still in two variable x and y cases. Second question, show that the mass of lamina is 128 over 15k. And next, find the y coordinate for the center of the mass of lamina. Well, let's look at the region. Now, I hope all of you should still be able to understand what does this interval means. Actually, from the interval itself, you can obtain 4 different equations. In other words, first question, y squared less than or equals to X less than or equals to 4Y. Cara untuk baca equation ini adalah ambil sebahagian kiri. This gives you Y squared equals to X. Take the right part. This gives you X equals to 4Y. So these are the two graphs that you need to plot. All right. Similarly, for the interval Y, this should be easy to handle sebab Y adalah constant interval in between Y0 and 4. All right. Again, read the left-hand part. This is just Y equals to 0. Read the right-hand part. This is just Y equals to 4. Now, putting everything on the graph of X and Y axis. And 0. Now, kalau X sama dengan Y square, you have to somehow keep track on your own. X equals to Y square is actually a C-shaped quadratic curve. Okay, sebab yang kuarter 2 adalah Y. So X equals to Y square is a C-shaped quadratic curve. Next, so let me jot down. This is X equals to Y square. Next, X equals to 4Y is actually a straight line graph. All right. Okay, maybe this graph is not so well plotted. Let me sketch in another more fancier and better way supaya kamu nampak curve di sini. All right. X equals to 4Y is actually a straight line graph passes through the origin. So somewhere looks like this. All right. So you will notice that there is one region bounded inside, which is actually this portion. And under this bounded region, there is one point of intersection and two intersection point. So there are 2 points of intersection. This origin 0, 0 should be easily recognizable. Now this part, it's probably where you need to slightly compute a bit. All right, under the graph, X equals to 4Y. So this is simultaneous equation. X equals to Y squared, X equals to 4Y. In the end, Y squared equals to 4Y. Doing a bit of rearranging, Y squared minus 4Y equals to 0. Therefore, factor out the Y. You have Y multiply Y minus 4, 0. Therefore, the 2 point of intersection adalah Y kosong dan Y4. So Y kosong dah ada, Y yang 4 adalah yang ini. All right, when Y4, X is actually 16. So this is just the graph of the region bounded by these two. So we have done for the first question. Okay, first question is simply to ask you to sketch the graph out and then see where is the boundary region. This is actually just like what we did in the previous topic in double integral, identifying the boundary region. Now, you don't have to worry. Most of the time, it has nothing to do with the integration of mass of Lamina. Okay, this bounded region, you do not actually need it to know the to compute the mass of Lamina, because the interval of X has been given, the interval of Y has already been given. So you just need to plug everything into the double integral. So this is what we mean next. Show that the mass M is given by 128/15K. So second question, if we want to compute the mass M, we are trying to find double integration of the density function rho with respect to area A. Now, the rho density function is given by K over square root of Y. This one. A, dA, I can simply put dx dy. Okay, why I put x in front? Because the interval x is already y squared to 4y. Well, you actually have the interval already, therefore just take the advantage from y squared until 4y. Y interval is from 0 to 4. So this is exactly how you can plug in everything immediately without having to worry too much about the computational steps. Okay, kalau kamu tak dapat nak bayangkan, dua-dua ini ibarat UV transformation. Kamu dah ada interval untuk X, dah ada interval untuk Y, then simply plug it into the double integral. Mana-mana yang function, wajib integrate dahulu. So that's why put dx inside because x is bounded by y squared and 4y. So after this, integrate with respect to x. So from 0 to 4, k over y square root is just a constant because we are integrating with respect to x. We obtain one variable x back. So substitute for y upper and y square below. So this gives you from 0 to 4, k over square root of y. Here, 4y minus y squared. Now, be careful. You have variable y outside here. Please distribute into it, open the bracket. Y variable yang sama wajib disimplifikan sebelum kamu integrate with respect to y. Remember this trick. So if you expand into it, y and square root of y can actually be simplified into 4k square root of y minus k over square root of y distribute into negative y power 2 actually gives you k y power 3 over 2. Ingat if you distribute 4y bahagi square root of y using power index law, y power 1 divided by y power 1 over 2. Kalau y yang sama, index boleh tolak sesama sendiri, giving you y 1 minus half equals to half. That's y square root of y. Similarly, here y kuasa 2 bahagi square root of y. This is just y power 2 divided by y power 1 over 2. Asas y sama, index tolak sesama sendiri. 2 subtract 1 over 2 is actually 3 over 2. That's why you have y power 3 over 2 here. Remember, if you have the same common variable, expand them, simplify the power before you integrate further. All right, so if you want, half is actually 1 over 2. Now everything has been done, you can integrate with respect to y. So 4k, y power 1 over 2 is integrated into y power 3 over 2 divided by 3 over 2. Minus k, y, 3 over 2 is integrated into 5 over 2 and then divided by 5 over 2. This integration substitute upper limit 4 and lower limit 0. All right, so substitute the upper limit into it a bit. So let's see how this is simplified. 4 divided by 3 over 2 actually gives you 8 over 3. K, y power 3 over 2, if you substitute by 4, will be 4 power 3 over 2. Minus k divided by 5 over 2 can be simplified into 2 over 5k, and then 4 power 5 over 2. So this is the substitution of upper limit minus, if you substitute lower limit 0, you will get 0. Now try to simplify this whole function. Eventually, trust me, you will get 128 over 15. Okay, so for this part, I will leave it to you to compute yourself. Provided you understand how the integration works so far, in the end, substitution of upper limit minus lower limit can be done using the help of your calculator. So for the next sub-question number 3, you want to show that the y-coordinate, or to find the y-coordinate for the center of the mass of Lamina. Similarly, try to write out first the formula for coordinate y. So this is given by y bar equals to 1 over m, the double integration of variable y multiply density function, and then with respect to area A. Now, previously, we have computed 128 over 15k to be the mass of Lamina. Therefore, this is just 1 over, in the big bracket, 128 over 15k. Double integration, let's say, once you've done n, whatever integral that you use here, you simply copy and paste it to the coordinate from 0 to 4, from y squared to 4y. Right? dx dy, well, you still fix it. The only part that you have to be careful here is y multiply density function, because you have the additional y variable, and the density function is given by k over square root of y. So something you can actually simplify here first. Number 1, k and k can be eliminated. Second, y multiply 1 over square root of y. Using index law, you can actually simplify this structure, giving you in the end here 15 over 128, double integral from 0 to 4, from y squared to 4y. Y and square root of y gives you y power 1 over 2 dx dy. All right, so let me work on one more step for you to see, and the rest I will leave it to you to continue the journey of the computation. So first thing first, we are integrate with respect to x. Y power 1 over 2, not related. Integrate with respect to x, return variable x, upper value 4, lower limit y squared, for y and y squared, dy. So this gives you 15 over 128, integrate from 0 to 4, y power 1 over 2 in the big bracket, 4y minus y squared. Now, using the similar technique, please expand everything first from outside to inside. So next step, you should obtain a more clearer and simplified version. Integrate from 0 to 4. Y power half multiply 4y gives you 4y power 3 over 2. Minus y power 1 over 2 multiply y squared gives you y power 5 over 2. So from here, you can next perform the integration using normal power rule. So for this part, I will leave it to you on your own exercise because I believe whenever the setup at the upper part has been resolved, if you understand that, then the rest is just the integration computation. Now, just want to convince you and clarify further, in the mass of Lamina, basically the solution, it's not really that challenging. All right, if you look carefully, we are just setting up the double integral and perform integration with respect to xy, yx, or r dr d theta. The only thing that you may find challenging in mass of Lamina is the working process of finding the integration. Yes, you will notice that along the process of integration, you involve a lot of power fractions, 1 over 2, 3 over 2, 5 over 2. It is this kind of power that will slightly makes your integration a bit messy and confusing. Therefore, take some time and patience, do the integration properly. So the rest of the exercises can be done in the similar way. So usually in the final exam questions, mass of Lamina will appear in part B. Now in final exam, part B is considered moderate. The challenging difficulty is still moderate, boleh buat, tetapi ambil masa yang lebih sedikit sebab ada banyak working step yang kamu kena berhati-hati, kena pay attention untuk elak kesilapan. So this is in part B in final exam. Now, this is the second topic in the tutorial session. The last subtopic actually taken from chapter 3. Okay, now this is chapter 19. In chapter 19, we learn about gradient, divergence, and the curve cross product. Yes, in this session, first tutorial session, I want to strengthen all of you with the concept of calculating gradient, divergence, and curve because they are the core of the vector calculus. Okay, fast recap. First, gradient. Gradient is the partial differential of function f with respect to each variable independently. Given one function of variable x and y, you find out the gradient by differentiate that function f with respect to x and differentiate the same function with respect to y. If the function is having x, y, z variable, then you just further differentiate with respect to z to get another gradient. In other words, gradient is a vector. Next, curl. Curl is certainly a vector function. So whenever you have the curl f, vector f, this curl means del cross. So whenever you have the del cross or cross product of f, be careful. This is the setting. First row should be direction ijk. Second row is actually the notation of del. Just to make sure you remember, del means differential with respect to x, differential with respect to y, differential with respect to z. That's why in the second row, you see the exact same notation. This is del. Last row is function vector f, m, and p. So once you can set into the curl 3 times 3 matrix determinant, then the computation is just a practice that you need to keep on doing it until you're familiar. With one extra part, you have to be careful. J direction is always minus. So this is the part I will still emphasize again and again later, that J direction for the curl is always negative. Finally, divergence. dot product. Okay, divergence, this term div by itself means del dot. So whenever we have dot product, we are multiplying component to component. Del multiply n over del x. Del multiply n over del y. So that's why you add both the result in the end. For 3D, del n over del x plus del n over del y plus del p over del z. Finally, add them up. So among, again, gradient, curl, and divergence, gradient is a vector, curl is a vector, divergence is a function or value. So understanding this, then in the next example, I will use the past year question just on last semester to go through with you. Now, some of you may have already practiced this question before, but for those who are not, then this is the kind of questions you will see in final exam with respect to curl, divergence, and gradient. Now, given function f in x, y, z 3-dimension, xy minus cos z, I minus x exponent z cos y j plus 2yz squared sine xk. This is a vector field. Questions: determine gradient of divergent f. Now, we also learn in the class, in vector calculus, sometimes we will combine several computations into one, like in this case, gradient of divergence. Now, to do this kind of operation, make sure you begin from the right-hand side, shift backward. Gradient of divergent f means that we do divergent first. Okay, sliding from right-hand side back to left. Now, since the first computation is divergence, so divergence tells us the dot product. So of vector f by vector notation, first component is xy minus cos. Sorry, should be dot first. Okay, again, div f is actually del dot vector f. The del here is actually vector differentiate with respect to x, differentiate with respect to y, differentiate with respect to z. Dot the vector f. Vector f has three components m and p. First component, xy minus cos z. Second component, negative x exponent power z cos y. Be careful, if there is a negative sign, bring along into your component. Component z, 2y, component p, sorry, 2yz squared sine x. So by the divergence computation, component multiply component. In other words, you will differentiate with respect to x. What is x, y minus cos z? Plus, you differentiate the component second, dealt with respect to y. What is negative x exponent power z cos y? Plus, finally, del over del z to component p. Differentiate with respect to z. What is 2yz squared sine x? Now, we will always provide you quite a complicated vector function. Make sure you can identify the correct variable you want to differentiate. So you are differentiate with respect to x here. So xy is differentiated with respect to x into y. Cos z, 0, because cos z has nothing to do with variable x. Therefore, this is the first result. Plus, differentiate this function with respect to y. Yes, I have a cos y here that I can differentiate. So negative x exponent z not related, put aside first. Differentiate cos y gives me negative sin y. Again, dalam partial differentiation yang tak berkenaan, letak di tepi, differentiate yang berkenaan. So finally, here, differentiate 2y z squared sin x. 2y sin x not related. Let me put aside first. So z squared is differentiated into 2z. So now you can simplify everything. Y plus negative becomes positive. X exponent power z sine y plus 2y sine x multiplied 2z 4y z sine x. So this is the divergence of the vector f. So after completing the right-hand side, then only you shift backward to the left, finding the gradient. Now finding the gradient, grade of the divergence of vector f is simply finding differential del of this function. All right, now to make everything simple, let me denote this as phi. Okay, again, to make everything simple for you to see, let me put f as this whole string first. Okay, kalau kamu tak letak f pun tak salah, tak let pun tak salah. But here, just to let you know, later when you find the gradient of the divergence of f, this divergence inside is what we computed here, which means we are now computing the gradient of the function f. This is to say that we are going to differentiate this function with respect to x. This function we differentiate with respect to y, and the same function we differentiate again with respect to z. So let me continue this on the next blank slide. All right, rewrite again the function so that you can keep track. Just now, the divergence that I computed, y plus x exponent power z sine y plus 4y z sine x. Okay, now computing gradient. Grad f. So first thing first, differentiate with respect to x, this whole part. So this is with respect to x, comma, oops, before that, close the bracket, comma, second, differentiate with respect to y, the same function again. Comma, finally, differentiate the same function again, now with respect to z. So this is the part that you have to be careful because the result of the divergence is actually quite lengthy. Make sure when you perform the gradient computation, don't get confused and don't do any careless mistake. Now close the vector. So now differentiate with respect to x. Y, nothing to do, 0 plus x exponent power z sine y. Yes, I can differentiate x here. Therefore, it gives me exponent power z sine y. plus 4yz sine x. Yes, there is a variable x. Therefore, put aside 4yz, tak berkenaan. Differentiate sine, you get cos. So this is the first gradient with respect to x. Second, you now differentiate with respect to y. Well, y differentiate with respect to y, you obtain 1. Plus x exponent z sin y. Yes, ada sin y di sini, maka letak x exponent kuasa z di tepi, differentiate sin y gives you cos y. Plus 4yz sin x. Yes, I have also y there, therefore I put 4z sin x beside. Differentiate y, you get 1. So just nice. And finally, differentiate with respect to z, y not related, 0. Here, x exponent z sin y. Okay, yes, there's a variable z here, but x sin y tak berkenaan, put aside. Differentiate exponent z, you still get back exponent z. Okay, this should be x, not z. And finally, 4yz sin x. Ada juga z, therefore 4y sin x yang tak berkenaan, put aside, differentiate z, you get 1. So in the end, this whole long string is the gradient of the divergence of f. This is the only thing that you try to obtain in the end of this computation. So you just need to be careful, do slowly, make sure every term that has that particular variable, you differentiate partially correctly. So again, like I mentioned in the class, gradient, divergence, and curl usually will be asked in part A in final exam. Again, part A is considered easy question. In fact, all the operation here is easy. The only one makes it difficult is the function is longer and more complicated. All right, so there's one more last question for the first tutorial session today. This is also the past year questions in February 2025. If you look carefully, it only grants you 5 marks. So here you want to prove that the divergence of the curl of function vector f is equals to 0. So this is the function, so this is the vector f given, and this vector f has component 3x, y, z for n, x, z over 5 for n, and 5y, z power 3 for p. Again, divergence of curl, which means we perform the curl computation on the right-hand side first. By the curl of vector f, this is the setting of 3 times 3 matrices, I, j, k. And the second row, differentiate with respect to x, differentiate with respect to y, and differentiate with respect to z. Finally, last row is the vector component n and p. So by the curl computation in the bracket, arrow bracket notation, to compute the I component, this will be differentiate 5yz power 3 with respect to y. So I have 5z power 3 minus differentiate xz over 5 with respect to z. I have x over 5. First component. Second, comma, negative in the bracket, differentiate 5yx, 5yz power 3 with respect to x, 0, minus differentiate 3xyz with respect to z. Yes, I have 1, therefore 3xy. Lastly, for the direction k, differentiate xz over 5 with respect to x, z over 5, minus differentiate 3xyz with respect to y, 3xz. So this is the curve. Simplify it whenever possible. 5z power 3 minus x over 5. Negative gives you positive 3xy. And z over 5 minus 3xz. So we have done the curve on the right-hand side. Finally, shifting to the left-hand side, divergence of the curve. All right, so here the divergence of the curve of the vector f. This means that we will have differentiate with respect to x, differentiate with respect to y, differentiate with respect to z. Divergence means dot the curve that we computed here. 5z power 3 minus x over 5, 3xy, and z over 5 minus 3xz. Again, under the divergence computation, component multiply component. First component, differentiate 5z power 3 minus x over 5 with respect to x. 5z power 3 with respect to x, 0. Minus x over 5 with respect to x, 1 over 5. Plus, next different color, red color, differentiate 3xy with respect to y, 3x. Plus, last color, blue, differentiate z over 5 minus 3xz with respect to z. Z over 5 with respect to z, you obtain 1 over 5. Minus 3xz, you obtain minus 3x. Now, eventually, you will notice that negative 1 over 5 plus 1 over 5 eliminated. 3x minus 3x eliminated. In the end, yes, I have shown that this divergence of the curve is equals to 0 as requested by the question. So this is again a small demonstration about the core concept of the vector calculus, gradient, curve, and divergence. Okay, I hope this additional tutorial session with more questions discussed should give you wider idea about how each topic can vary the questions from one to another. All right. The most important part is you need to understand the concept first, what you are doing. Next, use the correct formula or expression to solve the problem. For the case of integral, make sure you integrate the function with respect to the variable correctly. If you are differentiate partially, make sure you differentiate with respect to the correct variable. Any non-related variable in integration, you put aside. In differentiation, you assume like a constant. So after this, if there are more questions that you practice on your own and you need help, just let me know from time to time. All right, that will be enough for this first tutorial session. So in the next tutorial session, we will focus on the conservative vector field and the line integral if possible. So that's it. Thank you for everyone attending the session. I will now stop the recording and later upload the recording session in the YouTube as usual. Any help, any comments, just let me know. Till that, thank you and have a good night. Bye-bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
All right, no problem.
Thank you,
no
sir.
problem, no problem.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
All right, you're welcome, everyone.
Thank you, sir.